camera.
Yeah. Doc cam and everything worked.
Yeah, it worked, right?
Yeah.
Right. If I go PC, yeah, but see, if I go, it should be projecting now, right? Yes, that's not gonna work, right? I have to share screen to make it work. Does everyone agree to that? It worked before.
It worked
right?
the first 4 or 5 times.
So you're
you
saying
did
it's
it.
got to be when I plug my computer in it? But
I mean, that's
I
what I
didn't-
was saying, because that's the only thing that you did different.
no, then the first day though, I didn't plug in the computer and it didn't work. But I don't remember if I hit record or not.
Maybe he literally thinks that the video of that screen will be enough for you to see later what was done on the screen.
I don't know. I guess the only way to do it is to try it without class. But the thing is, like when I record, it takes it like an hour to get to send the file. So I think I'm going to do share screen.
I mean, is anybody on the Zoom call right now? Because there's only 4 that see it now. 5.
One. Well, someone's going to look at it later on, maybe.
What I'm
So-
saying is that whatever you're recording is probably what they're seeing, right?
Yeah, I can. Yeah.
You got it.
Okay,
Yeah.
so should I do share screen or not? Or what I see, what do you see now? Yeah, that's a good point.
She's logging in.
Yeah,
Okay.
I'm pulling up Zoom.
It's recording now, right? I think she's seeing what Zoom meeting shows, right?
So yeah, I mean, I see that.
Okay, now wait a minute. Don't do anything. That's on. Then. Wait, it's not doing it yet. Oh, it says wait. Because that thing's warming up. How do you see that?
I do see the document cam.
Okay, so you don't record, so he's right. I mean, you don't share screen, you just do whatever. All right, we've resolved something. That's good. So, let's see. We had a couple more just in case.
But you know, I bet it was sharing the screen, but it was like, instead of sharing the screen, it's probably sharing one tab or something. Or like just this, you know.
I think they need like an idiot guide, like in big red letters. It's probably there, you know, always when I say that, it's like right here. Like, I look over, oh yeah, they did that. It's just very, they didn't plan for such a level of idiocy. So, all right, so I think we've kind of beaten this thing to death, except C star. The RG functionality, everyone got that. I guess that's the Chi thing. That's the Fourier-Krigbaum equation. Someone didn't put that in. And then, but this one's C. So this one, so C, some of you guys didn't, the undergrad guys didn't get it right. Guys and gals. So, because I want to go to the. So you have this plug I, plug Q. This is one of the size. This is kind of like mass. So mass goes with size to the dimension. In other words, if you have a rod, mass is proportional to size. If you have a disk, it's squared. So if this is 1 over size, that means this is like size 1 over. Or size, 1 over size to the minus df. So this slope here is minus df for power 1. So if you take log of that, the df comes out into straight line. So then you have this region where you have good solvent. Or It's going to go to -2. That's fine. Erase gyration for the coil. This is this thing we call the blob size. And you found out that as the temperature dropped, the blob size got bigger. And at the same time, this coil size got smaller because this is denser. It eats up into that, just like when you heat a thing, it kind of crumples. Then somebody said, well, this is like 3D, which is not right. So this is 2D. So both of these are like nebulous, kind of crinkly things. 3D would be like that. Right? So it's not 3D. It's still got a density that changes with size. So the density drops dramatically with size. If you have a short rod and you spin it around, if you have a big rod and spin it around, this definitely has less density. Right? So it's not a 3D object. And this transition goes that way because this is denser, this guy has to go that way. And also because it becomes denser, this guy is how many times number of the contrast squared. What is this drop? Someone said the contrast changed. I guess that must be what it drops. This drops, that's true. That wasn't part of the question, but a couple people mentioned it. That drops. Let's see, does that have to drop with RG? Not really. There's a mass and the number should stay constant. RG should just shift over. This guy should just shift to smaller sizes that way. As the 2 beats up more and more. So I'm not sure why that drops. That drops in data. Shouldn't drop. Should just stay the same. It's just how many when they're kind of contrast squared, because you have contrast between two things. So it's squared. And this is just if you put in twice as much, you get twice the intensity. So I'm not sure why that drops in the thing. Anyway, that was part of the. That was one I wanted to go through, even though it was kind of quick. And something else. Oh, and then this thing magically, it's like almost a match. It doubles and goes in half, so it perfectly matches it. Which wasn't. I just found some numbers on the internet. So it's like it wasn't planned that it would match it. So that's pretty good. So it turned out to be a pretty good question by accident. So anyway, that's that business. Any questions on that thing? I thought it seemed like you guys did a pretty good job on it. It was good to map out like how that. Oh, there is one other thing. Yeah, and I wanted to try to do this to show you how that plot. No one did that plot. The first group of grad students gave the numbers. So I plotted that. It kind of worked. This will work. So where it is. Digitized homework. Bunch of graphs. Here. So if you plot from the first, whatever group it was, there was like 3 people, Sharon and some other people.
Oh, we plotted it, but we got a
You
power
guys
law because we
plotted.
didn't
Yeah,
put one
yeah.
over.
You didn't do the 1 over plot.
No.
Right. One of the groups gave the numbers, but didn't do the plot, I think. And the other group gave the plot.
What plot is it?
The blob size versus temperature, and it comes out kind of curved a little bit.
I gave it.
But if you plot inverse blob size versus inverse temperature,
Comes up pretty straight.
yeah, it's pretty straight, and you can extrapolate down. This should be the Kuhn length. That comes out to be 60 angstrom. the cooling for PMMA is 17 angstrom. And this is PMMA with a bunch of these side chain things on it, so it could be longer.
So you can't see this screen when you switch over to your other computer.
Oh, that's interesting.
It just says it's just a green screen.
I see. Well, that's all right. At least I know that. That's good. Thanks for letting me know that. Anyway, so wait, it is a straight line pretty much, given that we kind of guessed the numbers. This one, when you go down, so you end up with a temperature over here. That temperature is minus 73 centigrade. So that could be the UCST temperature. It's about, but then one of the groups mentioned that the solvent, the oil they're using crystallizes at 20. So you can't reach that LCST. So the only way to measure it would be like an extrapolation like this. So the two limits of this are kind of useful. They can kind of say what the system's doing. Anyway, I wanted to show that. So I wonder why that doesn't work. I'll ask the UCIT guy why that doesn't work. He seems to have all the answers. But then he got confused. He said that this wouldn't work if you didn't. Anyway, he gave the wrong answer the other day. Let's see. I'm gonna hide this PowerPoint here. This is weird. Oh, here, they're all here. Okay, so I'll open that. Open. These two are what I need. Do that because I want to go through the other kind of blobs. So there's three kinds of blobs. I mean, there's more than three. There's like 5 kinds of blobs, but we're going to talk about 3 of them, 4 of them. Yes, well, cone length is kind of a blob. So you see, there's this kind of symmetry to blobs. So you have like a small sizes, you have a rod. That's the step length. And then at large sizes, you have power 2, Gaussian. Right? And then you can say, for the stenciled blob, when you stretch it, you get a rod at large sizes, and at small sizes, you get 2. So like you're stretching it out, just it's harder and harder to stretch the small things because the lever arm's smaller. So you're trying to pick a little teeny thing and straighten it out versus a big thing where you can just grab it and straighten it out. Right? So these things are symmetric. You know, you have 1, 2, 2, 1 as you go in size scale. So something like almost like a rule of nature that there's going to be some symmetry to these things. You can find one kind of transition in size, the other one probably exists too. And the logic is going to be like you apply a force like externally and grab it and pull it. The other one you apply it internally like the bonds and you pull it. So you can apply a force to a hierarchical structure. You can apply force locally or you can apply it globally, and the effect's going to be the same but upside down in size. That's a postulation. I don't think anyone else has postulated that, by the way. I just made that up. So it's kind of like, I think it's kind of true though. All right, so we have the thermal blob where we saw it collapses like when you burn the plastic, it melts locally to make this Gaussian, and then at large scale still a wouldn't walk. And then there's another one called the concentration blob, okay, which is what happens when you get above C star if you're in a good solvent. Right? And you can have both of these at the same time. Right? You can have a thermal and a concentration. You can have all of them at the same time. Right? But basically, it's better to think of them one at a time. Right? But basically, what happens is you go above C star, and then you can't see the coil anymore, right? Because you have the situation. So you have your coil, you can see it, it's got the size R. Right? And then you get to C star, right? And then all of a sudden, if at C star, you can kind of see R. But above C star, R doesn't exist anymore. You can't see it because the things overlap with each other. So at that point, if you look at a small scale, you see the same thing. 5/3. You have the 1.72. And then at large scale, the thing is it's the same thing as with the device screening with the gun thing. So you have like guns going off all around you, you don't know where to run. Or even guns become like an AC humming if you get things there. Right, so at large scales, you effectively lose the enthalpic interactions altogether, and then it just becomes Gaussian. So it's just like device screening, except it's structural. It's a structural interactions. It's enthalpic interaction. It's not this charge thing. Right, so it's pretty close to device screening. See, it happens at large scales above kind of the cutoff size, which would be like the Debye one. But you call it here the blob size, the concentration blob size. So if you plotted this log I versus log Q, you see like a steep part, -2, and then we go shallow, -5/3, and then we go to 1. So shallow. Okay, so we go, you can see this concentration blob size, and as the concentration went up, this guy would eat up more of the chain. This thing gets smaller with concentration. This thing should get, as concentration goes up, this thing should go down. It should become smaller because it's going to eat more with this tube into the thing. And this part remains the same, so you'd see, and our G should remain the same. So this, in other words, this n squared n should remain the same. This 2 should just march over and eat up more and more of that. So that's how the R gets smaller overall. The dense part becomes more of it, and it uses out this kind of expanded part until it reaches this Kuhn length, and it stops there. Right, so that's how you go. So if you're in this region, so if you're at C less than C star, you're in dilute. If you're at C, like greater than C star, but less than when this thing equals the Kuhn length, less than some other concentration, then that's called semi-dilute, because it has this kind of behavior that's going on. Right. So this can all be figured out. Okay, like this is something that can be solved because in the region where you're in this semi-dilute region, then the coil size is not a function of the molecular weight. So you can get a scaling law out of that.
I'm not sure I want to do that derivation because it's messy and it's written here somewhere. That's kind of a picture, another picture of it. So I had this all worked out. Maybe I have it in there. Step 1, 2, and 3. But I can remember because this isn't done in step 1, 2, and 3. I mean, the first step is to say, let me go back over here.
So the first step is to say, so you want to get, what you want to get is that blob size is a function of concentration. You want to get the coil size as a function of concentration. So, and then the concentration, you realize at some point that the concentration by C star becomes the important parameter. And C star is the mass of the size cubed, and this is the expanded coil size. So that expanded coil size goes with m to the 3/5, or 1 over 1.72. Where it's this thing to the dimension would give the mass, so 1 over the dimension mass is that thing. So instead of m, I'm going to call this n. N to the 1 minus 3/5 cubed, which is 9/5, gives you n to the minus 4/5, or n to the minus 0.8. Because pi times 2 is 10, pi times 2 is 8. So that's the dependence of C star. So C over C star has this n to the 0.8 dependence. And then then we have that, then there's a bunch of other rules that you have, because you have the blob size of the thing. Is going, so you're gonna have like, so each of these, so this is gonna have these blobs that are 3/5 or 5/3, and then they're connected together into twos. The whole block is 2. So the concentration, and then within each of these is going to be an NC, and then of those is going to be capital NC. Those little NC, big NC is going to be N, that same N here. So this thing divided by the Kuhn length is going to be little NC to the 3/5. You also have the rule that big R is going to be big NC to the 1/2 times this thing, because that thing becomes a step size of this big one. And we want to get R in. So then we have the C star definition. There's one other thing that's missing here. Let's just notice. There's one other rule that I put down. It's easy to forget. Oh, you can write this one right away. That one you can say right away here. Go back here. So also you have that this thing's not a function of n, and also this thing's not a function of n. Right, so if that thing's not a function of n, let's see, hold on a second. Oh, wait, I don't know. All right, so also you can say that R is going to be dependent on C over C star. So you reduce C by C star to some power P. And then R is going to be dependent on n to the 1/2. R is going to be, because the original R excluded volume. So R excluded volume times C over C star over P, and excluded volume is going to be n to the 3/5 times C by C star to the P, and C by C star goes with n to the 28. So that means, or 4/5. You have n to the 3/5 plus P times n to the 4/5. And that thing has to equal 0 because it has to be equal to n to the 0 power. And so then you can solve for that P. So the 5's cancel, and then you have P is negative 3/4. So then you can solve this thing like what's R's dependence on, what is R's dependence on concentration with this blob thing? Let's just solve from that, because you have the n to 3/5, and then this becomes so you can see. Well, the dependence on C is just n. So n doesn't depend on C. You have C to the -3/4. It's R depends on concentration -3/4. Just from that thing. So you can solve that one pretty easily. And then once you have that, then you know this thing. So you have the R dependence. You want this dependence. And C dependence. NC depends on n at NC. So if you have little NC, let me see how you do that.
This is kind of involved to do if you don't have it written out. So this thing, this we wrote, right? We have C star -3/4 times R gives that. I did that backwards.
What do I do? End of the one, NC to the 1/2. R is expanded coil C by C star.
Oh, this is just writing that the other way. Let's see. I messed this up. This is Oh, I said that wrong. I said that R was going to depend that way, and I should have said that it was the blob size that depends that way, because the blob size, when C equals C star, the blob size is the expanded coil size. This is the right thing. So, and then you say it has this power law dependence, and you solve for P, it's minus 3/4. This thing is the expanded coil times that thing. And the expanded coil doesn't depend on concentration. So it's this thing that depends on the 3/4 thing. And then, sorry about that. This is kind of confusing. Then once you have that thing, you have the equation for the blob size, which is the blob size goes with this guy, the number of units in a blob to the, those are each good solvent blobs. So they're 3/5. So it's going to be this 3/4 law and then the 5/3 to remove that dependence. You end up with this blob, number of units in a blob goes with concentration of the 5/4 from that. Like the threes cancel, you have 5/4. And then once you have that, so you know the blob size scaling and the number of blobs scaling, then you can get the R scaling because R goes with the number of blobs times the blob size and the square root. So you just plug that in and get this minus 1/8 for R. Sorry about that. So that's it. You have the blob scaling, and you have this R scaling. All right, so you have both of those, and you can, all right, so how do you verify that? So you can get those by, this is called a scaling law, right? So there's no prefactors, just saying kind of how the behavior would be roughly, right? So how do you verify that? So there's a problem with this, that
Say you did neutron scattering, right? So you have your independent coils, you're in dilute. So you get this log intensity, log Q thing, and you get minus 1.72. So that you can do because you have contrast for each of these. Once they come to overlap, then you lose the contrast with that size scale. So this thing just cuts off. There's just nothing there because so say this is like, say you have like a fleece like this, right? It's made up of little fibers, but when you look at it, it's just a black sheet. You can't see any structure, right? But if I zoom in, I can see the fibers, right? So that's the same thing happens in scattering. You look out, you see the fleece. Then at some point, if you zoom in enough, you see the fibers. Right? So there's a cutoff point, and the denser the non-woven, the smaller the sizes. You can't see the fiber at. So as the concentration goes up, that thing just eats out. You see nothing there. So you can't see that too, it's invisible. Because the idea of structural screening is you can't see it. That's the idea that once it overlaps, it becomes just uniform to you. But that size scale of viewing. It's just like you look at the table, it's a table, you don't see the atoms because you can't see that small. But if you zoom in, you can see atoms. Right? So it's the same kind of thing as that. All right, so that's called screening. And it basically means that you can see nothing. So the only way to see this is you take one chain and deuterate it, right? And then the rest of it, and then you just look at that one deuterated chain and the sea of the other chains, and you can see the scaling where you find out where this had gone down, then you see this -2 shows up. With if you use the red, so you deuterate, put deuterium instead of hydrogen. The contrast is the highest of anything for neutrons. So you can only do this with a neutron scattering measurement. Or if you could conceivably do it if you took like chlorinated polyethylene, including with polyethylene, because chlorine has an X-ray contrast. So you could do it with X-rays, but chlorine is quite a bit different than hydrogen. It weighs more, it's charged, it's got a lot of differences. So you can possibly do it that way, but the easiest way to do it is just deuteration. So that's how it's done. And then this was verified. That was verified with neutron scaling. But that's true. And also the scaling predictions you can kind of measure with rheology. You can say like, I mean, like you can measure the intrinsic viscosity for the solution, or you can kind of say that has something to do with the structure and measure the size from that. So it's possible to do it with rheology too.
But basically, the way to measure that is neutron scattering. That's the simplest way. So So that's those four kinds of blobs. We went through the, whatever that is, right? It says tensile, thermal, concentration, and then the Kuhn length. I guess are four things. Right, so we'll talk about some other kinds of blobs. I mean, the blob idea really came from the guy Rouse, who took the chain, like he was calculating what the flow would be for a chain. He broke it into subunits called Rouse units, but the scale, there's no scaling difference between the chain and the Rouse unit. So it was a blob in the sense that he renormalized the chain into these subunits, each of which was a Gaussian spring, and dragged like a dashpot. A drag coefficient is Stokes' law because it's a sphere. And then you could figure out how the Polymer chain moved, right? So the idea of breaking down a structure into a hierarchy like that existed before this business came along in the 1970s about how to describe these transitions that are going on within a coil. Anyway, that's probably one of the more complicated things to hear about. This character Dowd was pretty famous, and Cotton, both these guys became famous, French guys. So even though the guy's got an English name, so I never could figure that out. Dowd is like a Turkish name or something, I think. I don't think that's French, but anyway, they were in France. It's like outside Paris, and then they wanted to look at these this kind of star polymer. What's the structure of the chain, and they sorted out that as you go across that, if it's got enough functionality to it, you have a concentration gradient as you go out from the center, if you have a core to the thing. And they came up with this Dowd-Cotton theory for star polymers about out here it's an expanded coil, and here it's a Gaussian chain. And across that, you can calculate what the thickness of that chain layer is in the thing. So this is similar to like if you have I mean, the motivation for that is if you can buy silica, for instance, and then particles that have grafted polymer on it to add to tires to fill it or for other applications. A lot of people are like gluing chains onto different things to make it compatible with the polymer matrix. So anyway, the motivation for that is partly that, and partly this idea it's pretty easy to make these star polymers. And then once they could make star polymers, they started making dendrimer polymers. We can make these kind of arboreal, close arboreal, tree-like things. And those became products. So those product lines are arboreal urethanes. Arboreal urethanes, like BSM makes it. So product line of or something. Some kind of thing. So anyway, there's a whole family of these topological polymers that are commercial products. So anyway, the Dowd-Cotton stuff fits in with that. I mean, it turns out the Dowd-Cotton model isn't really right. Basically, it's the accepted model. So don't move with that. If anybody asks about star polymers, the first thing you say is Dowd-Cotton model. So we went through thermal blob. That's the same thing. And we don't want to talk about this now. I want to go over to 3. I guess I'll rearrange the slides because this is 3.
You were on 3.
I was on 3. Oh, then I want to go to 2, I guess.
You also have a 2 part 2.
Yeah, I got to rearrange these things somehow. This is like a mess here. I did that. Actually, I had this all planned out on sheets of paper at home. I didn't bring them, but it's all right. This is just, so there's 2 things that happen, right, with this. Let me just say this. So this is a good plot. So you have specific viscosity. So it's solution viscosity of a polymer in a solution minus the solvent. And then you divide by the solvent, you get the specific, right? And when that's 1, that's supposed to be the entanglement concentration for the chains entangled. So that's double. That's when you double the solvent viscosity. You can see it isn't like perfect, but that's the general rule. So, and this is unitless because you divided viscosity by viscosity. So people think about these things, you know. One thing they think about is if you say, so this kind of defines something like an overlap concentration, I guess here. So you could say, well, the overlap and this entanglement are the same thing, right? They kind of look like the same thing if you take a quiescent view of the world. As you say, like the minute that these things touch, well, they must entangle at that same place. That has to be the same concentration. So say C entanglement equals C star, right? And then like recently, people have said, well, maybe that's not true. People become interested in extensional flow, which happens when if you have two pipes, so you have 4 pipes set up, you pipe in here, you pipe out there, exactly at that spot, you have extensional flow. So the chains are happily tumbling along, and they get to this point when they're ripped in 2 directions at once. You know? So they kind of straightened out. So if you think about that, then this definitely is not true. Because once the chain isn't quiescent, like just a blob thing, and it stretches out, then it could entangle a lot earlier, you know, like, because it's bigger, like it becomes larger, it's possible to interact with the chains earlier. Right, so there's a question, is that true or not? So that question was addressed by these. It's just, and also the other point is that for polyelectrolytes, is that true too? So like polyelectrolytes are different because they have these charge interactions. So it could be that it's different. So anyway, these are metaphysical ideas. This is what happens when you go, so you have 1 million, this is a high molecular weight, like 4 million is pretty high. You have ultra high molecular weight polyethylene, which is like a truck bed liner or a coal sheet, because it has incredible abrasion resistance. Also hip implants, right? So normal polyethylene is 100,000 grams per mole, and that stuff's 10 million or something. What is it like? It's really high. You can't extrude it. So in order to make something with it, you have to do like rotational molding. You put all the powder, you take it above the melting point, put it all into a barrel or something shaped like a swimming pool or a truck bed, and then roll it around until it coats it and kind of melts together. Then out pops a truck bed somehow. They do it at Wyandotte.
Oh, we don't even do ultra high liquid. There's only like.
There's a company like Zimmer or something in northern Indiana that does the hip implants. That uses their,
So then do they have to like machine it after that fact if they want it not?
I'm not sure you can machine it because it's abrasion resistant. Like you can pour coal down it forever and it will never wear away. So I mean, how are you going to machine it? I don't know. It'll heat up, it'll burn probably before you can machine it. So anyway, it's pretty interesting stuff, you know, considering. Also, that's what so you can make a gel out of it and you can spin the gel, and that's how you make bulletproof fiber. It's stronger than steel. So that like the racing sailboats, the sails are made of that stuff too. Anyway, this is that stuff. That's just an aside, right? So this is 4 million molecular weight. It's huge, you know. It's polyethylene oxide. It's not polyethylene. So it's dissolvable in water. When they spin it, so this kind of effect happens a lot more when you have a high molecular weight. It has more room to like deform, right? So the small ones probably won't deform much. In other words, it's the same idea. There's no lever arm. You have a small chain, it's going to be really hard to straighten it out because each unit has KT. You're fighting against that. But if you have a huge chain, you got a gigantic lever arm and you can take care of KT really easily. You know, it's going to just straighten out. So this is an example. So he's got a concentration. Some of these are really low, like 0.05. Oh, this is the time. 0.2 weight percent is pretty low. But some of these are really low. Lower than that. Anyway, even with 0.28%, so that the overlap concentration is going to be like kind of like 1%, you know, so he's 5 times lower than that, yet he still can get a fiber to form when he has extensional flow. So it's in other words, extensional flow is like when you extrude a fiber and then you pull it onto a reel. the problem is that reel has to turn exponentially faster and faster to get continuous extensional flow. So you only can have variable extensional flows. It's hard to study. That's why you go to that jet thing, 2 things in, 1 thing out. So extensional flow is really important to processing, but it's really hard to study in a lab. So people have been like working on how to study it. So it becomes a topic people are interested in, like 2006, I guess, whatever. McCosco is like the leader of this kind of processing, polymer processing stuff in Minnesota. One of his students was out at Cross Moffitt. He was like a run in their research, whatever product development stuff. But then he quit. So I don't know what happened to him. But basically, there was a McCosco guy around here. But anyway, so it's just showing. So they do this kind of capillary flow measurement. They measure the diameter of the capillary as a function of time. And then they plot that diameter ratio from the initial one. So 0 is when it matches it, and then it decays as the flow goes on with time at different concentrations. Then they get a relaxation time from that. Like how fast does it fall as some exponential? They get relaxation time, which is kind of like the viscosity, the extensional viscosity of the thing. And then you can kind of plot that as a function of concentration, and then find out that there's an entanglement effect before you get to C star. So they can get C star from some other method, like light scattering or something. Then they can see that this entanglement concentration is different than C star. Right. So that's it. I mean, that's kind of like a non. I mean, basically, you kind of would anticipate that, but they demonstrated it. And so. This is this relaxation time or the viscosity for a SAOS is a oscillatory shear. It's a normal thing with the cone plate oscillating. So that's a quiescent measurement, viscosity kind of. And then this is this capillary thinning. They get a lot more bump out of it. And this is kind of the number that's important if you're spinning a fiber or blowing a film or doing some kind of processing where you're kind of tearing apart the polymer. Right, so it's a lot different number. The behavior is quite a bit different. So it's important. This that business. This is the guy Colby at Penn State. So he wrote, him and Rubenstein. There's a book, Polymer Physics, on the web page you can look at. But anyway, they did a lot with polyelectrolytes. This is a picture. This is like a picture. This is a pretty good picture of what's going on. Like you have a good solvent, absolute volume, theta. This is collapse. We'll talk about that soon, sometime. This is what happens when you put a charge on it. You get almost a rod out of it. Right. So the things are different. So he's got here. So this is C star versus molecular weight. And I said before that would be 4/5. Right, and then 0.8 is 4/5. 2 times 4 is 2 times 5 is 10, about 0.8. So that's a normal slope you expect for C star. So red circles are a neutral good solvent entanglement concentration. So when you do that viscosity measurement, like where does that cutoff happen? The concentration where that cutoff happens versus if you can measure the coil size and then the coil mass, and you can calculate the C star. So they're 2 different numbers. I mean, for a non-charged normal polymer like polystyrene and gasoline, right? So napalm. So that's going to be basically, they have the same good solvent scaling for C star and C entanglement match, but they're different numbers. Maybe that makes sense. I mean, it depends. CE is higher than C star, so that means it takes more oomph to get an entanglement than it takes to get this overlap, which kind of makes sense. I mean, you have to, for an entangle, they have to actually penetrate, and maybe when they just touch, that's not enough. So that's the concept behind those 2. So the interesting thing is that when you look at a polyelectrolyte, blue circles is this entanglement for polyelectrolytes. It's the same behavior as the neutral, right? So the entanglement is acting as if it's a Gaussian coil or a self-avoiding Watt coil, okay? And then there's this -2 for the C star polyelectrolytes. So this -2 comes from this. So if you take the dimensionality, so C star equals the mass by R cubed, and R cubed is the mass to the 1 by df to the 3. This is mass to the 1, so you have mass to the 1 minus 3 by df. When df is 5/3, that gives you 1 minus 9/5, which gives you m to the minus 4/5, which is m to the 0.8. If df is 2, you get m to the 0.5 minus 0.8 minus 0.5, because you get 3 halves from 1, so it gives you 0.5. So where does this minus 2 come from? Well, if it's a run, then df is 1, you have 1 minus 3 by 1 is 3, so it's 2. M to the minus 2 for a rod. Right, so when you're looking at, so blue stars are polyelectrolyte C star. So the overlap concentration for polyelectrolytes, they act like rods. Right? And then circles are the entanglement. So the entanglement, they act like coils. Right. So that's puzzling. And Colby's a pretty good guy. Colby worked in industry, worked like Kodak or something in New York. He was like Cornell PhD, and then went to Kodak or somewhere. Worked there for a while. And then he went to Penn State. So like he's been there a long time. Basically, he still seems like a young guy, even though he's been around forever. You know, it's kind of funny. And he still has like, because of that, people like don't trust him kind of. He's almost like a rebel type in that. So old school rheologists like Ron Larson, Michigan, they're like, oh, Colby, you know, so it's kind of a funny thing. But anyway, it turns out like he's done a hell of a lot more than any of the other guys, but they don't, there's a lot of things like that happen. So anyway, so there he is. He's got this thing that doesn't make any sense. I'm not sure he explains it this way in the paper either, but this is the way I interpret this, all right, so if you look at why is this thing acting like a good solvent, it's because the entanglement molecular weight is looking at something on a different size scale. Okay, so in fact, like when you do a rheology measurement, you're talking about like centimeters, you know? So you're looking at a bulk sample, and you're looking at like how these things like entangle with each other on a centimeter size scale, maybe millimeter, right? But C star is looking at like nanometer. Right. So there's two different things that you're measuring. So it can be a random walk or a self-avoiding walk on a centimeter size scale made up of rods on a nanoscale. So if you look at C star, it's rods. If you look at this large size scale, this macroscopic measurement you're doing, even though it should reflect the same thing, you're seeing a completely, absolutely different behavior. It's kind of interesting. I mean, it just shows you that you shouldn't, you have to be careful about what you're talking about here. You know, like you have to, the measurement you're doing defines what you're measuring and the behavior you're seeing. So it's acting like a good salt, like a random walk here at large size scales because it's making a network that percolates, and that's what you're measuring. And the other one's measuring this kind of microscopic thing going on.
Where the polyelectrolyte just is kind of
It's
like
a rod. They're
that's
just rods, yeah, because the persistence length is huge. So they're just, but they actually are taking kind of a random walk on a large scale, right? So they kind of couple up. And then anyway, somehow it works that way. That's my explanation for it. You can read this paper. I think it's on the web page, how he explains it. It's a pretty long paper, right? So plus 20 pages, you know, where he's trying to explain the entire behavior of the universe here, you know, which is typical of a Colby paper, you know, but it's good. Like he's right. I mean, and the measurement's really intuitive, like unexpected, you know. So 2010 stuff. He goes through a lot of business in that paper. We already talked about LCST, UCST kind of. Oh, I didn't bring that. I was going to bring some of this PDME, but I didn't. This is what I wanted to get to. So probably, why don't I go through this twice? Because this is a mess. And I can go through it in 5 minutes, and then I can go through it again, you know. So there's a book, this book, Giant Molecules, is on the web page. So it's like almost like a book that it was intended for high school students or maybe grammar school students. Because, all right, but you got to be really careful, especially in this field, because those books are like the most difficult and complex books. You know, it's like the hard ones, you can't read them, so it's not going to hurt you much. But the ones that he starts out like saying, "Oh, look at this big floppy," da, 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 and like it's like a teddy bear, da, 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 da. And then like you go into it, and then you realize this guy's like insanely talking about something. I don't have any idea what he's talking about, right? So you have to be careful. But that book is here, so just click on it and put an F. It's Grossberg. He's the guy that came and interviewed here, you know, and he ended up like he's at Harvard now. Like, and they didn't offer him a job, so it's kind of like he came and he gave like 3 lectures here. Yeah, it's right. Giant Molecules. This is just like a little paperback book. It's in the library. Look at it, but it's like chapter. It's like somewhere 127. I think I was looking at it. I think it's like this chapter. No, it's after that. It's a pretty good book, you know. It's just like I said, it's deceptively complex. This is there's a guy named Ferris, and I went to grad school, Dick Ferris. He's dead now, but he had one of these in his lab, and we used to call it the Ferris Wheel. So, it's like a tire. It's a bicycle tire with rubber bands. You know, when you heat a rubber band, it shrinks. So you can put the light on it, and because of that, and it cools down and expands on the other side, so the wheel will like turn. Like you can make a little motor out of that if you want. I thought that he invented it, you know, but he gives it someone else. Moscow State invented it. It's probably one of these Cold War things. Anyway, there's a chapter on this collapse transition here. It's after that. No, I guess it was 227. It's like this stuff. Maybe I don't know. Anyway, it's in the end. It's a pretty good book. It's worth glancing at, kind of fishing around a little bit. So let's see. I want to go back here. So he's talking about like what happens on this side. Like, so we have this completely explained by Floyd Krigbaum. Then the blob theory, the thermal blob theory explains what's going on. Then the theta state. And then there's this part, which people are interested in because it's like protein folding. So mostly biology, right? Or if you're in that part of the phase diagram where you're below C star and the coils are isolated but have to phase separate, that happens also. Like they have to collapse onto themselves, make a 3D blob kind of. All right, so in that region, there's 2 things that can happen. In fact, so they talk about it in terms of first order or second order transition. So first order means that there's a heat associated with the transition. So you have like an enthalpy of melting or enthalpy of boiling. Right? And it also means that there's a step change in the volume. Like when you boil, the vapor's got a huge volume and the liquid has a small volume. Right? So that's a first order transition because the thermodynamic parameter like density goes through the roof all of a sudden. It goes infinitely changes. Second order is like glass transition. So like the structure of a liquid and the structure of a glass are the same, indistinguishable. The only thing that happens is that the things get stuck. Right, so it's second order because it's only the slope of like the thermal expansion coefficient changes, that applies. But the volume actually is just continuous through the density. And so anyway, so this is the way they show it here, this is continuous, right? In other words, it looks kind of steep, but basically it's a continuous transition for a synthetic polymer. For a protein, it would be going along and then all of a sudden it would fold and it would just take a dive, like immediately it would have a step change. So those are like 2 fundamentally different kind of transitions. So he explains it. So I'll go through this like on Monday. I think we're out of time. I just noticed it. And Mike like moving his stuff, so that means must be time. Anyway, so yeah, we'll go through that. I'll have something on Friday for the homework thing.
So do you see both just in different
Yeah,
scenarios?
yeah, you do. In fact, here, since you asked, so you can do an experiment where you can take these two polymers, this is Penny Pan. This has an LCST. This guy also has an LCST. They're almost the same thing. This one's first order, and that one's second order. So yeah, you can see it.
And they're not really like, they don't look that different.
They aren't that different. Yeah, there's just a slight different. It's like a quaternary amine and a ternary amine or something. Like, yeah, so basically, yeah, people have studied it, you know, like anything else, so. Right. Oh. I think I just shut this down.
I know. Shannon and I, when we were going through the thing yesterday, when you had